guys, this video is for section 1.3 in module 1. So we are talking about foundations of functions in this unit, and specifically module 1, we're just going to review how to simplify radical expressions. So one thing to remember is that we have some notation here. So this is a radical. If there isn't a number out in front of the radical, we are going to assume it's a square root, which means we're looking for the number times itself twice that equals the number underneath. This part underneath here is called the radicand. And then this symbol is the radical. So radicand, sorry, that doesn't look like it. Radicand and radical. Okay, so we have a couple properties we're going to use to help us simplify. One is the product property, and it says the square root of a product is equal to the product of the square root. So I'm actually going to show the algebra here first, you guys. So if I have the square root of two things being multiplied together, and I'm just using a and b, they can be anything, I can actually split that apart into two separate square roots, and it works both ways. I can actually start here and combine it back underneath into one. So those are saying the same thing. I can go either direction. So numerically speaking, I could have something like this. Square root of 2 times the square root of 3. I could combine that underneath one radical. 2 times 3 is 6. I could also break apart a radical. So for example, if I had something like square root of 8, square root of 8 is the same as square root of 4 times square root of 2. And square root of 4 is just 2, a regular whole number 2. So I could actually rewrite this as 2 times the square root of 2. So I can pull it apart into two different products, or I can combine it into a single product, whatever is most convenient and depends on what my goal is in simplifying. Quotients are very similar. So again, I'm going to start with the algebra. So if I have the quotient, which means division of a fraction, I can separate that into two separate square roots. And again, this works both ways. Okay, so for example, if I have the square root of 9/16, okay, I can separate that into the square root of 9 over the square root of 16, which square root of 9 is 3, square root of 16 is 4. Okay. Similarly, I can combine into one, let's say I had something like this, square root of 32 and square root of 8. I can combine that into just square root of 32 over 8. Square root of 32 over 8, well, 32 divided by 8 is 4, so this just becomes square root of 4, which is just a regular 2. So simplifying as far as we can, sometimes it's more beneficial to separate, sometimes it's more beneficial to combine. Okay, so when we want to simplify, we want to pull out any perfect squares, and we want to reduce fractions where we can. So here, if we have just a single expression, I want to pull out any perfect squares. So when you guys looked at this in previous courses, you looked a lot of times at two methods. So I'm going to show you both ways on here. So the first one I'm going to do is I'm just going to come up with two numbers that multiply together to be 32. So I'm going to do 4 times 8. And I'm essentially creating a factor tree. So, and then I want to break these two numbers down into more factors, but not to the point where I would go to 1. So 4, I can break into 2 times 2. 8, I can break into 4 times 2. And then 4 again, I can break into 2 times 2. So once I've broken down a number, I'm not going to use it. So I'm actually going to cross those out. And what I'm looking for is pairs. So if I have a pair of 2's and a pair of 2's, that means I'm pulling two 2's out front of the radical. And if I have more than one number, I'm going to multiply them. So this 2 here, this 2 here. Anything left not paired goes underneath the radical. So I have this one lonely 2 that stays underneath. So if it's not a pair, it stays underneath the radical. Again, if I have more than one number that's not paired, I'm going to multiply them together there. So total, this is going to become 4 times the square root of 2. So this is considered simplified because I've pulled out any numbers that I can. Another way to do this is the perfect square method. So I want to think about the biggest perfect square that goes into 32. So perfect squares are numbers that we can take the square root of and get a nice whole number. So perfect squares are 1, 4, 9, 16, 25, 36, on and on and on. Okay, so I want to think about the biggest one that goes into 32. 16 is the biggest square root that goes into 32. So I'm just going to kind of do this separately here, you guys. So I could rewrite 32 as 16 times 2. And remember, we can break that apart. So square root of 16 is 4. Square root of 2 is not a perfect square, so we're going to leave it. So notice I got the same thing, which I should, but two different ways to go about it. So the factor tree, or I like to call that the buddy method. We're looking for pairs or buddies of numbers. This is just called the perfect square method, looking for the biggest perfect square that goes into that number we're trying to break down. Okay. I'm going to jump down to the multiplication one. So a couple options. You can simplify each of these first if you can, or you can multiply together first, then simplify. Doesn't really matter, you're going to end up at the same place. I'm going to actually go ahead and multiply these first. I'm going to combine it into 1. So 3 times 12 is 36, and 36 is a perfect square. Square root of 36 is just 6. Okay, this one, square root of 25 over 36. I always like to check, can I reduce those fractions first? In this case, I can't, so I'm going to go ahead and separate it into two separate square roots. And the reason being is I know I can take the square root of both of those. Square root of 25 is 5, square root of 36 is 6. Okay, here, I'm going to look at it as one fraction here first, you guys. So I'm going to combine it into 5 over 500, and the reason is because it's a little easier to look at the fraction here and reduce it. So 5 over 500, I can divide both those by 5 and get 1 over 100. Okay, and now 1 and 100 are two perfect squares. Square root of 1 is 1, square root of 100 is 10. All right, okay. Couple things, I've already filled in the blanks here, you guys, so go ahead and copy those down. What it says is if a fraction has a denominator that is a square root, it's not considered totally simplified. So we have a process called rationalizing the denominator. And what we're going to do is we're going to multiply the denominator by itself so that it ends up being a perfect square. So let's take a look at this. So this is not considered fully simplified, having that square root of 2 in the denominator. So I'm going to multiply both the top and the bottom by square root of 2. Why is this legal? Well, if I multiply anything by 1, it doesn't change the value, right? So this is essentially 1, square root of 2 divided by square root of 2. So I'm not changing the value of this expression, just changing how it looks. So it is a viable algebraic step. So multiplication, I get to go straight across. So I get 3. I cannot multiply the 2 times the 3. It's not under the radical, but I can multiply the 5 and 2 because they're both underneath the radical. So then I get square root of 2 times square root of 2 is square root of 4. Now, by multiplying by itself, what will always happen is we are essentially squaring that, right? So another way to think about this is the square root of 2 squared. Well, square rooting and squaring are opposites, and so we're just going to end up with that number underneath the radical, not squared. And then it's just a good idea to check, you guys, this is still a fraction. Can I reduce 3 over 2? There's nothing I can take out of both of those, so this would be my most simplified answer. Okay? All right, let's try this on I guess I don't have numbers on this second example. So I'm going to multiply by the square root of 8 to get the square root of 8 out of the denominator. These are both radicals, so I can go ahead and multiply. Square root of 16, and anytime I multiply a radical by itself, I'm just going to be left with what's underneath. The squaring and square root property are going to cancel. Square root of 16 is 4. And then 4/8 I can reduce down to 1/2. Okay, the other operation we're going to do with radicals, you guys, is we are going to add and subtract. So this is really helpful to think about radicals as like terms. So here's some examples of like terms. So square root of 3 and square root of 3. So if I wanted to add those, it's kind of like adding x plus x. Those are ones in front, essentially. So that would be 2, sorry, I didn't give myself enough space here. So square root of 3 plus the square root of 3, just like x plus x, I just add the coefficients and the root 3 stays the same. So root 3 plus root 3 is 2 root 3, okay? We can subtract if they're alike. So if I have something like negative 2 times the square root of 5 minus 3 times the square root of 5. So as long as what's underneath the radicals match, we can do the operation with the coefficients in front. So negative 2 minus 3 is negative 5. Again, I did not give myself enough room here. So I get negative 5 root 5. So whatever is underneath the radical stays the same, okay? Sure, we'll give one more example. If I have square root of x, 3 times the square root of x, minus 5 times the square root of x, that's going to be negative 2 times the square root of x, okay? So unlike terms are things where the radicals do not match. So square root of 2 plus square root of 3, I cannot do anything else with that. That is the most simplified version. Okay? Even if I have a 3 out front, I still cannot simplify those. Even though they involve the same numbers, whatever is underneath the radical has to match. Let's do one with subtraction. So if I have 8x minus 5 root y, cannot combine because the radicals do not match. Okay? All right, so let's apply that property here. Right now, the radicals match. They are alike. We can go ahead and do the addition. So 9 plus 7 is 16, and then I have the root 3 attached. Right now, these ones do not match, so as it is, I cannot subtract. However, square root of 20 is one that I can simplify further. So square root of 20 is the same as square root of 4 times 5. Well, square root of 4 is 2. So 2 root 5, if I did my operation with 20, square root of 20 simplified, now my radicals do match, so I can do the subtraction. So 6 minus 2 is 4, and then I have the root 5 tacked on. Okay, that is it for this video, guys. Thanks for watching.